Hello friends, so in the continuation of CTQ 12, in this video we will see the generalized structure and we will learn how to calculate the input and output impedances and also the gain calculation. So these are the two possible circuits that we always see with the op-amp, that is an inverting amplifier and one is a non-inverting amplifier. So the previous question in the previous video, we directly calculated whatever was asked there in that question, means output voltage, input, and output impedance. But here we will see something extra. In this particular, we'll use the concept of negative feedback as well. Okay. So the negative feedback concept, which we also discussed in CTQ 11, we'll use that thing here so that you can have good understanding or better understanding for this question as well. Okay, so when we talk about any impedance, what we in general do, we simply apply a test voltage or test current source at that node and we simply find the impedance. So we generally knows whatever we used in the previous question as well, either we'll use some VT source, means test source, and we'll compute current. So Vt by It will give me the impedance. And other way, directly apply a test current, which we call It, and observe the Vt at this node. So in this case also the impedance comes to be Vt by It, and here in this also the impedance comes out is Vt by It. That you can call RTH or whatever, R out if it is output impedance. It can also be R in if it is at input node. Whatever we can call it. Okay. So we'll see one by one what the possible discussions can be carried out here. And the negative feedback concept is very important. And this concept we'll use three things we already discussed in the question number 11, CTQ 11. We'll use the complete open loop gain. Then we'll find the beta. And after that, for closed loop gain, we simply use this AOL divided by 1 plus beta AOL. Okay, this is the general concept that we use to calculate the closed loop gain, and this is nothing but a DC closed loop gain. This is the DC open loop gain. Okay, so we are talking about the DC values only. Open loop uh, gain value. Okay, so we want to discuss about the DC things only. So these are two structure. One we call, if many of you will know or maybe may not, it is called inverting amplifier using op amp. Inverting amplifier. Both are in the negative feedback configuration, and one is inverting, other is a non-inverting amplifier. Non-inverting amplifier. Okay. So we'll discuss few extra things here. That first structure, that I call it first, I call it second. First structure is also current to voltage conversion. It is doing what? It is doing current to voltage conversion. Okay, and that current that I call I in is nothing but function of my V in. We'll see all the points in detail. Okay, so let's take the first circuit one. Before directly going into the input and output calculation, we see some extra things here. So what I told you, this is my amplifier. What it is doing, this node is at ground. Here I told you that it is nothing but a current to voltage conversion. So let this is my current IN. If I want to convert this current to the voltage, what we'll do? We will use some resistor here that I call R2, and this R2 will give me the V out, simply because this current will follow the path. If I assume that there is no impedance inside the amplifier, sorry, if there is no current going inside this amplifier, which is actually the case because the input impedance is too high, so it's zero impedance inside, then complete I in goes this way. If virtual short is applicable, this node X, if I call, Vx is also to be 0. And what you can see, V out is what? V out is Vx minus I in R. From here we can simply compute if my Vx is 0 because I am considering virtual short is there. So what it will be 0 minus I in R2. Okay. So simply what we can see V out by I in is nothing but minus R2. So this is the current to voltage conversion is happening. Now let's think if my this I in is nothing but a function of V in, then we can simply find V out by V in. Nothing but it is a gain of the inverting amplifier. What we have. Okay. So let's do this thing. So what is actually happening here? Okay. So if I'm considering again my amp is ideal, which I call if A to be infinite or virtual short is applicable, then what is happening? How I this current is generated? I will say this current is generated using some resistor and voltage. Okay. So this is my input current that we have taken in previous diagram here. This In is what? In is nothing but V in by R1. If I am considering that A is infinite, virtual short is applicable. If the node Vx is to be 0, then what is your In? In comes to be V in by R1. This is the current. Now if I want to convert this current into the voltage, we'll use some resistor and we'll fed a structure like this. Okay. So this is my output. Then what is the output value? We can see the output comes to be it is Vx0 minus R2 times I in, which we have seen already. So minus R2, what is the I in? I in is nothing but V in by R1. So this way we can see for this inverting amplifier V out by V in comes to be minus R2 by R1. Okay. So this is the gain of the inverting amplifier. Gain of the inverting amplifier. So overall, what is happening here? It is a I think a current to voltage conversion is happening here. But current is a function of the input voltage. Okay. So this is the thing that we are seeing. If you want to generally use some different structures, then what I can say, this current source can also be replaced as a GM cell, in which this is my V in, and this current coming out is fed into this amplifier, and after that this current is converted into the output voltage using some resistor. And this is also the possible combination, and you can analyze this circuit as well. What is happening here? And I am considering the A to be infinite, the ideal case. If we are considering the case when A is not infinite, okay. So let again discuss this thing with a finite A. Finite again. A is not equal to infinite. Okay. The same thing is happening here. A in the previous here A is infinite. Calculations are like that. And if this is the case, then this is 0. This is my current In, which I want to convert into the voltage. So if I want this current to be converted into the voltage, what I will do? I will simply use a resistor which will convert it to the voltage. Okay. So let I call this Vx is the value of the node X or inverting node. So what you can see, minus 8 times Vx is giving me the output. This is the one equation that we can see. Okay. And one more thing is that output has different relation also. Output is Vx minus I in R2. So what is the Vx? Vx is nothing but minus V out by A minus I in R2. So let take V out on the one side, 1 plus 1 by A equal to minus I in R2. Okay. So V out by In comes to be minus AR2 divided by 1 plus A. Okay. So this thing we can see, we have seen. If here, we can think here, if my gain is very high, if gain is very larger than the 1, then what we can say, V out by I in comes to be minus R2, which was the case of the ideal amp also. Okay, that we have seen. The same thing again can be done when this current is implemented by using some resistor R1, and this is the V in. But here the current is not exactly like the V in by R1, rather it is nothing but a V1. Okay, so it is not only the V1 by R1, rather it is a V1 minus Vx by R1. Okay, so what is the I in here? I in here is V in minus Vx by R1, and this current is converted into the voltage with, here gain is the finite, V out equal to what, minus AVx is one relation. Another relation of that, V out equal to Vx minus I in 2. This is also your V out. Okay, so if we put these two equation 2, 1 equal to 2, and what will come here, minus AVx equal to Vx minus I in R2. What you can say, Vx 1 plus A equal to I in R2. So Vx can be simply written as I in R2 divided by 1 plus A. This is my Vx simply coming. Okay. So then what can be the I in? I in is nothing but V in minus Vx, which is I in R2 by 1 plus A divided by R1. From here we can easily find it. Okay. So what it will come? It will come V in minus, V in by R1 minus R2 by R1 I in by 1 plus A. Okay. So this is my I in. So if I take I in on one side, then what it will be, 1 plus R2 by A R1. If I am considering A is much greater than 1, and what it will be, V in by R1. So if I consider A is much greater than 1, then again we can see this thing here, that this term is negligibly small. Okay, so what we can see, this term is nearly to be 0. Again we can reduce the expression to I in y V in by R1. Okay, so all the discussion depends on the value of A. If A is infinity, or A is very greater than the 1, then our expression comes nearly when we are considering the ideal case. Okay, so the only point here to discuss is that we are considering that the input current is converted into the voltage with some sort of mechanism that we are using the feedback resistor R2. Okay, so here what we are seeing here, input has no direct relation with the difference voltage of the amplifier. Okay, so what is the vd nothing but v positive minus v negative for this amplifier. This is the difference voltage. Input has no direct relation with the difference voltage, rather the output is fed back at the node x, while input has some different node this. So overall we can say there is a current mixing happening at the input. Okay, current mixing is happening at node X. So this is one topology of the feedback network that we will discuss in the feedback concepts. But right now I want to say that when input voltage is coming as a part of the difference voltage, then what we can say, what is the difference voltage actually? Difference voltage is nothing but the difference of inverting and non-inverting terminals of this amplifier. So if at any one node the input is directly connected and other node is coming from the output feedback, and what we can see, the difference voltage applied at the input, so applied at the amplifier's input. What I mean to say, the difference voltage applied at the input of the amplifier, if any of this node out of V positive or V negative is my input directly, then we can say there is a voltage mixing happening at the input. That is the case of the inverting non-inverting amplifier. We'll see sooner. Okay, so we have seen both the ways. Again I will say, We can also see the things for the finite gain just by using some GM cell here. Okay, so the Vn cannot be directly there. Rather, my Vn can be far apart from the input of the amplifier. Okay, now it is far apart as it is coming the input of this GM cell, and this the current coming out of the GM cell is converted into the voltage using some resistor R2. Okay, so this way, what my inverting amplifier says, the current, which is nothing but a function of input, is converted into the voltage using some feedback resistor R2. This is the case. Okay, here what happens actually, the input has no direct connection with, I will say one point here, input of the system has no direct connection or relation, no direct connection or relation with the difference voltage at the input of the amplifier. Okay, so what we can see, if my input has means no direct relation with the amplifier's input, then we can say there is a no voltage mixing happening. That we will see in some feedback video in the input of the amplifier. Then we will say no voltage mixing. This is still new term for many of you. We will see it in some feedback concept there. Okay, so output is fed back at this node. VD is V positive minus V negative. The output, this V positive, nothing but a function of my V out, but there is no direct relation with V positive or either V negative with my input, so it is not a voltage mixing. Okay, now we'll pick the second structure, then we'll again analyze it and we'll try to understand that particular structure with a negative feedback concept also. Okay, what is the other structure? Other structure is a non-inverting amplifier. Okay, so what is happening here, this negative terminal, which is called the inverting terminal, is nothing but an effect of output is seen at that node, which we call the x, let's say. So what is the Vx is nothing but a function of V out. Okay, which is also nothing but a V negative. And what is the V positive? V positive is my input voltage. Okay, so what is the difference voltage of the amplifier's input voltage, that is called the difference voltage, is nothing but V positive minus V negative. So I can say amplifiers input voltage is the function of input voltage of the circuit, input voltage of the circuit, or I should say complete system, that is my Vn. Actually, what is happening here? Here is a voltage mixing is happening here. Voltage mixing is happening here. So what we call it? Voltage is converted into voltage. What was happening in the previous circuit? Actually, the voltage was converted into the voltage, but the main thing was we were generating a current, and the current was converted into the voltage using some R2. Okay, so this structure can also be seen like this way. Why I'm saying in this is my input R2. I think this particular structure we have seen many times in CTQ 11. Okay, so instead of output here, my output is here. So if I call this feedback voltage, and what is happening, this difference voltage is nothing but input voltage minus the feedback voltage. A feedback voltage is a function of the output voltage, which I call directive beta output. Okay, so this thing usually happens in the voltage mixing. Here input and output voltage is coming as a difference to the amplifier's input, So that's why voltage mixing is happening here. This structure can directly drawn as a negative feedback system. Okay, so this structure can directly be seen as a negative amplifier system or negative feedback system. Okay, this is my R1, R2, V out. Okay, so what I mean to say, in the negative feedback representation directly is the way where we use some summation sign. This is my input. This we have seen this thing in CTQ 11 as well, and this is my gain block, which is taking the difference voltage. So it is called difference voltage. Also call it error voltage. Okay. So this is our R2. This is the R1. Output is here. So this structure generally we see in the negative feedback configuration. That the point I want to tell you from very starting. We can represent the circuit this in this way as well. Okay. So what I mean to say, if we break the loop here, okay, we can break the loop here. Loop is broken here, and what we can say, let I call this node as VF. So if the feedback voltage comes to be beta times V out, what is the beta here? Beta is nothing but R1 divided by R1 plus R2 times V out. Okay. So what the error voltage then? The difference voltage or error voltage is nothing but V in minus VF. And what is happening to the output? The output is coming as A times the difference voltage, which is nothing but A times V in minus VF. And what is the VF? VF is nothing but beta times V out from here. Okay. So A V in minus beta times V out. What we can write it as A V in minus A beta V out equal to V out. Let's separate the V out on one side and V in on other side. So it is A V in, what it can be, V out by V in is nothing but A times 1 plus A beta. Okay. So this thing we directly see. So by complete structure analysis, we have seen that the equation coming is a divided by 1 plus A beta. And this thing I told you many times that when we write the representation, when we represent our closed loop gain, this is called the closed loop gain, and this is called the AOL, the open loop gain. So when we represent any negative feedback system, this is my block A, and this is the beta block. What we usually see, we always write like this. So this is the input, some positive sign, and beta negative feedback is there. Okay, so this is a structure when anything such is happening here. And what we write, what the open loop gain, that is the feed forward gain is also called A here, and beta is beta itself. So when we write the closed loop gain, we write the AOL divided by 1 plus AOL beta. This is a DC closed loop gain. DC closed loop gain. So here what I can write, A divided by 1 plus A beta, that thing I am getting here also. In this case, if I consider that okay, A beta is much greater than 1, that A beta is also called the loop gain, DC loop gain. This is called DC loop gain. This thing I have discussed many times in previous videos, DC loop gain. Okay. If it is very much greater than the 1, then what you can say, the closed loop gain comes to be 1 upon beta. Okay, so this thing we can see here also. What is happening here, if the gain is 1 upon beta, what is the beta? This is my beta is r1 by r1 plus r2. Okay, so if my A, which is called the gain or A beta loop gain, is much greater than 1, and what closed loop gain comes here, V out by V in is equal to what it comes, A divided by 1 plus beta. It comes as nearly 1 upon beta. And who is beta here? Beta is nothing but R1 divided by R1 plus R2. So the closed loop gain should come as 1 upon beta means R1 plus R2 divided by R1. It can be written as 1 plus R2 by R1. So what is the expression? This expression nothing but directly we can say when we see the means in non-inverting amplifier, we directly write like this only. Okay. So we have seen this thing many times. Directly we can write like this. If someone is asking you what is the gain of this non-inverting amplifier, we all know that it is directly V out by V in equal to nothing but 1 plus R2 by R1. Okay, so we have seen this representation of the gain many times, but there is an actual understanding behind it is that we can consider a negative feedback system, and from that negative feedback system, if we are considering the open loop gain, the feed forward gain, and the beta factor, and after that, if we are representing the entire thing, we can directly find the closed loop gain as the AOL by 1 plus AOL beta. If AOL beta is much greater than this 1, then we can see simply closed loop comes as the 1 upon beta. Okay, if the one beta is nothing but a 1 R1 divided by 1 R1 plus R2, if we are representing like a closed loop gain is a 1 upon beta, it simply means it can be written as the 1 plus R2 by R1. Okay, this is the directly expression we see here. And about the other structure that can also be represented, but it is not exactly the negative feedback system, but yes, you can represent and analyze this structure as well. In this case, it is grounded. So what was happening here? R1, this was my input. This cannot be directly analyzed by using the negative feedback, but yes, the structure that I want to draw for it as well, this way we can draw that this terminal is grounded and this is the output I am taking across the end of R2, this is the R1, so this is the feedback I am taking here, but it is not exactly the negative feedback system forming here because this node is not 0, actually this node is some value with the input voltage. Okay, so this is the input. Here we are feeding the input. So if we are feeding the input here, then the analysis will be different. Okay, so this is the input point. Now we can directly go from input to output to find the V out by V in, which is nothing but a closed loop gain. Okay, closed loop gain. Because what we are seeing here, the feedback is coming, but this means this network is extra. It is not means output is not coming back to the input. Okay, the one point that I can say, output is not coming back to the input. Then only you will say now there is a means there is a voltage means feedback. If my output is coming and some part of output is coming to the input, or if it is directly not coming, it should come as a difference of the amplifier, and we can represent as the negative feedback system with this summation sign, and some sort of the function of output is coming here, and here is the input, and this difference is fed back to the amplifier. Then only you will see there is a negative feedback, and with that negative feedback we can analyze the structure what we have seen in the previous page. Okay, but yes, this way you can see your circuit in a different way, different dimension, different angles. When we can see the analog circuits from different angles, then we can have the better understanding of their analysis. Okay, so I think this is enough for this video. In the coming video, we'll see this concept will extend to the calculation of input and output impedance, and better if we can use the negative feedback concept to calculate the input and output impedances. Okay, so thank you for this video. Thank you.